Будь ласка, Томас Вандра.
Okay, so hi, my name is Tomas Vondra, and I'm very pleased to be here for the first time in Ukraine in general. And I'm here to talk about a command which is new in Postgres 10, which is called query statistics, because I worked on that, and I'm still working on that. So I'd like to explain like how should you use that? Why could it be useful for you? I'm a long-term Postgres contributor, committer. If you are thinking about contributing to Postgres, chances are I'll be committing your patch. If you have any questions about this command or any other commands in Postgres, I'm happy to answer them either during this talk or at the after party that we are going to have, I think, right? So first thing is I'm not a native speaker, so if you don't understand something, just let me know, and I will repeat that with exactly the same accent, so you have a chance misunderstanding for a second time. That's how it works, right? No, really, I mean, like, if you have questions during the talk, please ask them right away. Don't wait until the end. My talk is usually like 40, 45 minutes. And I think we have like 1 hour in the schedule, so we have plenty of time. I'm happy to answer questions during the talk. Right, so this talk is already, I have it on GitHub, so you can get all the whole talk, the PDF, the source data and anything. You don't need to remember the link. It's always in the bottom part of the slide. So what are we going to talk about today? Well, first I will have to give you a very quick introduction into Postgres, how it does plan queries, right? How it actually decides which query plans to do. Very quick introduction, very basic stuff. We will see how correlated columns, like statistical dependency between columns in the table, completely breaks this, right? And if you are running with large amounts of data, chances are you already have seen this in production when the database misplanned the query and actually picked a wrong plan for the query, which usually means like query running for much longer than it should, right? Then we will get to the main part of this talk, which is the query statistics command, which is how you can instruct the database to collect some additional statistics about these dependencies between columns, and hopefully that will help the database to pick the correct plan. Currently, in Postgres 12, we have 3 different types of statistics that you can collect for the table. It doesn't solve all possible cases, but I will show you cases it solves and cases it doesn't solve, right? And at the end, we will see some future improvements, like what we are currently working on in the commit fests, what we already have patches for, and also things that we don't know how to solve, right? So this is very much like a research area. So if you have idea how to what to do, ideas about different types of statistics that you know from other databases or from like your studies or something, this is a very good topic for like your first patch. During this talk, I will use a very simple data set, which is a typical data set for statistical dependencies, showing actually the issue, and that's the zip codes, right? It's a very simple table, which has a first, it's like a postal code, which is numeric. I'm using for all the talks, I've given this talk in different countries, and in each country I use like a local zip code database because that's familiar to the people, to the audience. So I'm doing the same thing here. That's a wonderful opportunity to mispronounce names, right? So sorry about that. It has a postal code, which is integer. Then it has like different levels of regions in the country, right? So you have like a place name, which is the smallest area. Then we have state name, province name. I'm not sure if that's like a correct translation for Ukraine. It might be like oblast, right? Like region, maybe. And then there are some additional columns like latitude, longitude. I'm not going to use these for this talk. In the GitHub repository, you will see this definition of the table. And then there is a database of zip codes, which is downloaded from this link, right? And it has, I think, like 20,000 different zip codes. I'm not sure if that's like exactly correct for the current state, but it should be good enough for the examples. So that's what I'm going to use. I need examples, or I need data set with more data than this. So what I simply did, I have inserted the data again and again until I have a table with like 2 million rows, right? So because then I will be able to show you the misestimations very easily. That's what you would get, for example, in like a fact table in a star schema, right? You get like a lot of redundancy between the rows, and that's exactly what I did here, right? So the other thing I need to explain is what a command called explain does. In pretty much any database now has something like this. It simply displays the current execution plan, like how the database thinks it will execute the query, right? What it thinks is the most efficient way. So the most important part in this is these are different steps in the execution of the query. So for example, this is very simple. It's just a single step, which is a sequential scan. And the most important part of that is estimates and actual number of rows, right? So the first part is like rows 3, 1, 5, 4. That's what the database thinks will match the condition place name is with, right? So the database thinks it will find like 3,154 rows, and then it actually executes the query because I did explain analyze, and it actually found like 2,944, which is very close to the estimate, right? The database does the planning based on the estimate, and then at execution time, it either is sufficiently accurate or not. I will show you like different execution plans during the talk. These two numbers are probably the most important pieces of that, right? Because the reason why database picks the wrong plan is usually it misestimates something, right? It thinks it will find one row and it finds 1 million, or it thinks it will find 1 million rows and it actually finds a single row. And these are actually, this is a problem because in one case, an index scan might be very efficient, and in the other case, a sequential scan might be very efficient, right? I mean, that's what we use the estimates for. Right, so if I do a query like this, how does the database actually know where did the number, the estimate come from, right? The second number is simple. The database simply runs the query, and it knows how many rows it found. But the first one, the estimate, how does the database actually come up with the estimate? Well, the database has statistics about the data, right? So the first thing is it does know how many rows and how many disk pages a table has, right? So if you look into the main system catalog in Postgres, if you don't know any other system catalog, this is the one you know. which is like a list of all relations, all tables and indexes in the database. And for each one, the database has an estimate of number of tuples, number of rows, and the number of disk pages, right? So it kind of knows how large the file is in terms of like kilobytes, and it also knows roughly, it's not exact, but it knows how many rows are there in the data set. So in this case, it's like 1.9 million rows, right? Because I have created the table and inserted the data repeatedly until I get this number, right? So this is the first thing the database knows. So if you do just a sequential scan from the table, it will find this number of rows, and it will need to read roughly that amount of data from disk, possibly, right? But what about the condition, right? I mean, I did have a select from zip codes with a condition on a column which is called place name. So how does the database actually know how many rows match that condition? Well, the database also has statistics about distribution of the data, right? It has like a statistic distribution function of values stored in the column. And that's stored in another system catalog, which is called PG statistics, but there is like a very nice view, which is called PG stats, which is easier to read for people. And that has a number of different columns in that. The database collects statistics like fraction of null values in the column, number of distinct values in the column, right? So you know how many different values are there. It does have a histogram of the values. And what I will be working here is most common value list. It simply says like, these are the most common values and these are the frequencies, right? So if I run analyze on the table with the zip codes, then I know that Kiev is like 0.6% of the data, right? I know that Kharkov is like 0.3, Dnieper is like 0.3, and Lviv is like 1.6%, right? So that's the frequency of the data. The database simply samples the data and computes this frequency for each value it sees in the sample. And then it stores that in the system catalog. So it then can combine that with the statistics about like the size of the table, right? So if I get back to the original query, I know that there's 1.89 million rows. I know that that value, Lviv, has like this frequency. So if I multiply this together, I know that for Lviv, I should expect like 3,154 values, which is exactly the estimate, right? So the database knows this, then does costing of the query, like computes like how expensive that is to read this using like sequential scan, index scan, whatever, and picks the cheapest one. So that's how it does for one column. If I choose a different column, like instead of place name, I use province name, the database does in principle exactly the same thing, right? It has the same most common value list for the column, so it knows that a frequency of that value is 0.15. It does multiply that and gets like a slightly lower estimate, right? Which is, I mean, like not perfect because it's still based on sampling and so on, but it's still like fairly close, right? It's like 3,000 versus 4,000. That's usually sufficiently accurate for good query planning. When we say like misestimation in Postgres or in general, we usually talk about like estimates that are an order of magnitude different, right? So if I, instead of 3,000 rows, if I estimate like 300 rows, that might be an issue. But usually anything like a smaller error is usually okay. So what happens if I use two conditions together, right? Instead of like a condition on place name or a province name, what if I use them together in the same query? Well, the database will do a very simple thing. It will compute the frequency of the first condition, then it will compute the frequency of the second condition, and then it will multiply them together, right? And that usually leads to underestimation, because we know that Lviv is in the Lvivska region, and that like a large part of the region is Lviv, right? But the database has no idea. So it just multiplies that together, assuming independence of the conditions, and it suddenly thinks that there are just 5 rows. But in reality, it's almost exactly the original value, right? So that's one issue the database doesn't realize. And it happens because frequencies or the estimates are just probabilities, right? What's the probability that a given row, that a row matches a condition? And we have two conditions. The database thinks, okay, so I can just like, split that, multiply that, compute those individual probabilities, like one condition, second condition, and then multiply that. Which in this case means, well, we have these two conditions. Place name is Lviv, province name is Lvivska. Then we will split that into the individual conditions. We will compute the frequencies from the most common value lists for each of those conditions, multiply that together, we get this number. I'm not going to try to pronounce it here. We multiply that with the size of the table in number of rows, and we get like 4.78, which is rounded to 5. So we know that this doesn't like make sense in this case, because we know the data is there is statistical dependence in the data, but the databases don't know that, and the databases don't know. They have no concept of this like dependency between columns, because they simply just collect statistics for each individual column. They don't try to compute like correlation or something like that. So this is like a first error, right? So underestimation is the first case, but we can also overestimate things by simply inverting the condition, right? So when I say place name Kiev, but the province name is not Kiev, like it's some other region, well, the database will again make a mistake, right? Because we will think, okay, Kiev is like 11,000 different zip codes or rows. Province name is not Kiev. That's like 95% of the data, right? And if you multiply that together, you get like 12,000 rows. But the database doesn't realize those are actually mutually exclusive conditions, right? In most data sets, there's like a small set of exceptions, right? So you have like one part of the city accidentally, for historic reasons, belonging to like a different region or something. In this case, that's not true. And we get like 0 rows. But the database doesn't realize that, makes a mistake. So why does it happen? Well, the databases rely on something we call AVIA, attribute value independence assumption, which simply means that knowing a value in one column doesn't predict a value in another column, right? So if you know that which in this case is not true, right? Because if you know that the place name is Kiev, you know that the region or like any other part of the zip code record, you know what the value is going to be. The databases, however, rely on this because they don't have statistics about the correlations between the columns. And this can easily lead to both underestimations and overestimations, right? I have shown you like 2 different examples. And this, who actually investigated like a slow query, which turned out to be caused by misestimations. I'm sure you have done that. No one. Okay. I will assume that you chose to be incognito here. I'm sure some of you actually did investigations like this. So typically it leads to 2 different kinds of issues, right? So the first case is like underestimation. So the database thinks it will find like 90 rows, but it finds like millions of rows, right? This is made up example, but this usually forces the database or pushes the database to prefer plans that do random I/O. So for example, the database thinks it will find 90 rows, so it picks index scan, right? But then it finds like many more rows, and suddenly it would be much easier and much cheaper to do a sequential scan on the data, and that's it. So that's underestimation. Overestimation is the opposite direction, right? So the database thinks it will find like 12 million rows. So it says, okay, so I'm not going to do index scan. That will be pointless. So I will do a sequential scan, and then finds just 90 rows, and index scan would be much more efficient, right? So this is usually a worse case because this, the consequences are arbitrarily large, right? Depending on like what's this value, you can get like 10 times, 20 times, 100 times more expensive query. In this case, you will, once you pick the sequential scan, the cost is still the same, pretty much, right? So in my experience, like the underestimates are worse, but that's my experience. And of course, this is not like related to or limited to just the scans, the scan nodes, like index scan, sequential scan, so on. This also propagates through the query, right? So if you have a query which is joining multiple tables, and you do a misestimation at the bottom layer, like when reading from a table, it's very easy to actually cause like a sequence of, for example, in this case, if you do underestimation, you pick nested loop because the database thinks that joining like 90 rows is very cheap using an index scan, but it then propagates through nested loop, nested loop, nested loop, and this might be doable. You would wait for like an hour for the query to complete. I mean, like, but this as a whole has no chance of completing. But the database simply doesn't realize that, right? So how do you, how can you fix issues like this, right? So before Postgres 10, the only chance you really had was like fiddling with the options that affect query planning. Like, so either you've been increasing the CPU cost size or random page cost or something like this, or maybe you have been enabling, disabling different steps in the query planning. So if you have a query which has issues with nested loop, you might have disabled nested loop, for example, right? Which works, but it's problematic because it affects the whole query. So if you have like a query which needs like a nested loop in one part, but no nested loop in the other part, like different sides of a join or something, this doesn't really work, right? It's also like kind of heavy-handed because it doesn't, if you get like additional data, the query plan may change, or the most optimal way to execute the query may change. But if you disable a certain operation, that actually doesn't update itself with the data, right? So that's annoying. And in Postgres 10, we got some first additional statistics that, well, Postgres 10 added a command which is called create statistics. And it had some basic statistics about correlation between columns, right? And the first one is functional dependencies. The other one is end-string coefficients. I will talk about that in a minute. Functional dependencies is for conditions in the where clause. The end-string coefficients is more about aggregation, right? So if you have problems with like group by, that's what I will talk about in a few minutes. But let's talk about functional dependencies first. So I assume that you are kind of familiar with the concept of normalization, right? So if you have a schema, you know that you can remove redundancy or normalize the data, normalize the schema, which is essentially about functional dependencies, right? So if you know that a value in a column A determines value in column B, then either column A should be like a primary key of the table, or you should split the table into two, right? So a trivial example, primary key determines everything, but also there are other functional dependencies between columns in the zip code. So for example, if you know a zip code, which is the primary key, you know what's the place name, you know the region, you know the province, and so on. So if I give you a number like 4176, you know that it's Kiev, right? But there are also other dependencies. And for example, if you know the place, you probably know the state, right? If you know the state, you know the province. And of course, it's transitive. So if you know the place, you automatically know the province. So that's the concept of functional dependency. If you have like a denormalized data set, you almost certainly have functional dependencies in the data, right? And the database doesn't realize that unless you instruct it to collect statistics about this. So in Postgres 10, we have a new command which is called create statistics. It has a slightly strange syntax. I mean, you might initially assume it's like create index, right? Create index on and so on. That's not exactly the case here, because what we have here is create statistics, name of the statistics, types of the statistics we want to collect. In this case, dependencies mean functional dependencies. And then you have like a part of a query, right? So it says on columns from a table. The reason why it's done like this and not like create index is we want to support eventually statistics on multiple tables, right? So to help with join estimations. And that wouldn't be possible with the simple syntax, so we actually did this. So this will create the statistics on zip codes. And then if you do analyze, it will collect the regular statistics and this new statistics too, right? Just like you can inspect statistics using the pgstats system view or system catalog, we have a new catalog which is called pgstatistics extended. Extended statistics is the official name of the feature. And it will give you something like this, right? Which is like a JSON-B representation of the statistics, which simply says like which columns are functionally dependent. So the numbers here, which I have not explained before, that's the attribute number, right? So place name in the create table was the second column, state name was the third column, and so on. That's like internal numbers in system catalogs in Postgres. And that's what we store in the statistics. We don't store the attribute names, because if you change the name of the attribute, that would be an issue. But we store actually the numbers. And then this is like attribute number 2 implies attribute number 3 with a strength between 0 and 1. So why don't we have just strength as 0 and 1? Like, is functionally dependent, is not functionally dependent? Well, there are no perfect data sets, right? Each data set has a bunch of exceptions, either because of historical reasons, like regions changing between, or cities changing between region, or one city split across multiple regions, or something like that, or simply data entry errors, right? People do mistakes when they enter data. And what you don't want is wildly change the estimate based on the sample which is used to compute the statistics, right? So let's say you have perfectly functionally dependent data set with a single row which contradicts that, right? Because someone made an error when entering the data or something like that. You do analyze, and either you sample the row or don't sample the row. If you have like a perfect functional dependency and no dependency at all, those are pretty extreme cases, right? And you don't want that to be like to change the query plan significantly, right? Like a sampling of single row is like not sufficient. So that's why we have the strength. How exactly that works is like there's this formula which says like between 0 and 1, and for 0 it means like no functional dependency at all. We simply revert to multiplying the two probabilities, and for 1 we simply ignore the second probability, right? So if I say that the two columns are functionally dependent with strength 1, is perfect functional dependency, I will do like this probability times 1, right? Because this is like 1 plus 0 times the second condition. If there is no functional dependency at all, it simply degrades into this condition multiplied by the other condition. So that's like the very idea. And in this case, if I use the numbers from before, and I use the, this functional dependency strength, because place name implies province name, that's the functional dependency there. If I multiply that together, I get 2000, right? Instead of like estimate of 5, I suddenly get estimate of 2000, which is like very close to 3000. So great, that's fixed, right? Well, that's the only case that actually is fixed in this case, right? Because if I look at the overestimate, which I have seen before, there's province name equals Kiev, and state name does not equal Kiev. But the functional dependencies only really support equalities, right? So if you have conditions that are not equalities, we can't actually use those statistics at all. I'm not sure that's actually necessarily true. Maybe it can be done, it can be extended in this direction, but at this point it doesn't work, right? So that's one case. The other case is, however, like that's not what I have shown you before. This is overestimate where I use equalities, but with two different conditions, both equalities, but Kiev is not in Lvivska Oblast, right? So, and the database, again, doesn't realize that. And the functional dependencies actually don't really work here because the database doesn't realize dependencies between individual values. We only know that these columns are dependent, functionally dependent, and the database assumes that the queries are kind of consistent with that, right? So, for example, if you have a search form on a website, which you will pick like, say, state name, and it will pre-fill the provinces, then you are guaranteed that you only see like compatible values, right? But once the users can pick like different parts of the form independently, then suddenly this issue can happen, right? This is a limitation. The one reason why we have done functional dependencies in Postgres 10 is it's a very simple statistic, right? It just says like this column and this column are dependent with this strength, but it doesn't tell you like this value in this column implies this value in the other column, right? That makes it very cheap. It was a great statistics to use for introducing all the infrastructure into the source code, but it has these limitations. And I will show you how one of the statistics, well, the only statistic introduced in Postgres 12, which is the most common value list, actually fixes this, right? So that was functional dependencies, right? I mean, if you have queries that only use, if you have queries that only use equalities, and you know that you generate the queries in a way that respect the functional dependency, this is very cheap, a very fast way to essentially eliminate some of the conditions from the estimation, right? Right. So the other part of this talk is about ndistinct. And if you have ever done like analytics or BI or whatever is the current name for that, like essentially aggregating large amounts of data, chances are you have run into this issue, right? So first, let me give you some introduction how database does query planning of group by, right? So we have pretty much two different algorithms to do group by queries. The first one is hash aggregate, right? We simply build a hash table in memory, and we use that to accumulate all the data and build, the aggregated results. So, for example, if I have count, I will have a hash table with a province name as a key, and then for each different value of the province, I will have a counter which says how many rows I saw with that group, right? The other option is group aggregation, which means I have to sort the data first, and then I simply feed the data sorted by the group key through the aggregation, which allows me to only keep a single group in memory, right? Which means I don't need a hash table, I need a single group, but I need to sort the data first. And how does the database actually pick like which of those to use? Well, we need to know the number of groups in a column, right? Or in the combination of columns. So if I do group by province name, the database thinks, well, there are 522 provinces. And in reality, it's very close because it's like 524, right? So how does the database know that? Well, again, it looks into the pgstats or pgstatistic catalog. And one of the other statistics in that, we have already seen the most common value list, which says like frequencies of values. But there's also a column or statistic which is called n-distinct, which says like how many distinct values are there in the column. And for each column of the table, it will tell you this estimate, right? So for example, I see that province name is 522 rows or 522 different values, which is exactly what I saw in the estimate, right? So if I do the group by, I should get like roughly this number of results, which is great. Then there is like province name, right? Sorry, a place name is much more detailed. So it has like 17,000 different values because it's essentially like one zip code is one place name, right? So what if I do a group by with both columns? How does the database actually like determine the number of groups in that? Well, you can see that it's like suddenly thinks the data set is like 190,000 different rows, which doesn't make sense, right? Because the original data set has like 20,000 different rows, and I have multiplied that, like inserted it repeatedly. It doesn't make sense. I can't see more distinct values than that. So, and well, you see that it's actually like 27,000 different place names, right? So how does the database actually compute that estimate? Well, we kind of, again, assume independence. So if I see like 500 different rows, different values in one column and 17,000 different rows in the other column, we multiply that together and we say, okay, this is our estimate, which in this case is like 8.7 million or something like that. The database realizes it doesn't make sense to have more values than actually are rows in the table. And there's like a heuristic that we use up to 10% of the table in like this case, right? So we will use 1.8 million divided by 10, and that's exactly the estimate, right? Which is okay. The problem here is that instead of the, instead of the hash aggregation, because we saw like 500 different rows, which fits into workmem, so the database knows it will fit into workmem. This will not fit into the workmem of like the 4 megabytes that I had in the example database. So it has to switch to the group aggregate, which requires sorting, right? Which is, if you have a large data set, that's going to be slow, and it will require a lot of disk space because it needs to essentially spill all the data to disk to temporary files, which is annoying. In this case, it's spilled just like 90 megabytes. But if you have larger data sets, this is an issue. Right. So what you can do, well, we have a different types of statistics in Postgres, which is called n-distinct coefficients. You can do pretty much just like before, create statistics. This time you need to specify the type of the statistics as n-distinct. You can create both at the same time, right? You can list both dependencies and n-distinct. It will work. And then you do analyze, and then you can again inspect the statistics in the system view pgstatsxt. If you are on older versions of Postgres, this works in Postgres 12. If you are on older versions of Postgres, this command is slightly different. I can show you that later. But you will see a slight, quite similar output to the dependencies. It simply says like this and this column, when combined, it will have this many distinct rows. If you combine the other columns, it will have that number of distinct values, and so on. So if you have specified 3 columns, it will compute, the estimates, the coefficients for all combinations of 2 columns and all 3 columns, of course. So I did a group by place name and province name. So in this case, I think it's like 2 and 4. And if I do the query again, you see that the estimate is like not the insanely high number, but it's almost exactly the correct result, right? So it's like 26,500 versus 27,600. And the database realizes that, okay, so this fits into workmem, and it will use hash aggregate again. Right. So those are distinct coefficients. The old behavior is kind of defensive, right? It means like we will rather overestimate the value than underestimate the value. And the reason is we know that the computing the estimate from per column estimates without this new statistic is kind of really, really difficult. I mean, getting a good estimate is tricky, and hash aggregation in Postgres is about the only operation that can't actually spill to disk, right? So once you, we do consider workmem during planning, and we will not pick hash aggregation if we think it will not fit into workmem. But once we decide to use hash aggregation, we can't change it later. So if you use, for example, hash join, and you do underestimation during planning, we can still increase the number of batches during execution and still, keep the workmem limit, enforce it, right? But for hash aggregation, that's not possible. If you do a significant underestimation, and then you get like 100 times more groups during the execution, you can run out of memory. And we have no way to fix that. So that's one reason why we rather overestimated the value with the, multiply that and divide by 10 or something like that. Which is better than just crashing the whole database, right? The n-distinct coefficients give us like additional information and more trust into the estimates, so we can actually do the estimates and trust them more and pick the hash aggregation more often than before, which is nice, I think. This is especially useful for, again, large data sets like fact tables, which have a lot of redundancy between the columns. So, for example, if you have different column for different parts of the date, like, for example, year, month, day, whatever, this can be very, very useful. Right. So this was n-distinct coefficients, and most common value lists are a new feature in Postgres 12. It just gives you like a new type of statistic for that you can use in the create statistics command. And I will show you an example of that. So I have just a new cluster. Nothing is loaded into that. So we all know that demos work flawlessly all the time, right? So I will create a table. Create database. This is like a development version of Postgres. So I do S. So it's like Postgres 13, but really it's pretty much what you get when you install Postgres 12. Now I can do create table, which just creates the table that we have seen before, right? So if I do zip codes, right? So it's just a postal code. Well, I think I should have used integer for the postal code. Doesn't really matter here. Now I will copy the data set, which is like 30,000 rows. And now I will do the usual, what I have seen before. I will just insert data again and again until I have like 1 million 2 million rows, right? So if I do select count star, it's like 1.9 million rows. Well, now we are ready to do, I will do analyze zip codes. And I will run some of the queries that we have seen before, right? So this is the first example, which in this case, we estimate like 10,000, sorry. So that's the incompatible conditions, right? So I see like 10,000 different rows estimated, 0 rows during execution. Then the other query, that's the other counter example, which says like incompatible values with equality conditions. Again, I get like 800 rows, 700 rows estimated, 0 in practice. I could create the functional dependencies, but that shouldn't really help here, right? We will see the misestimations I've shown you in the slides. And this section is really about the most common value lists. So, well, let's try creating the statistics, right? So I will create the statistics on the 2 columns I'm interested in. I could create like statistics or additional columns, doesn't matter. I will do analyze, and that should collect and build the most common value list. When I say most common value list, I mean combinations of values from the different columns and frequencies for each of the combination. I can actually show you how the statistics, how the most common value lists look like, because there is a simple query. The simple query will be in the slides, right? So it simply inspects the statistics stored in the database, expands it into easy to read table representation. And you can see that I know that the first one is like 0.5%, the second one is 0.52, and these are the combinations, like, so we know that the different columns are, those are the different values from the different columns. And there are 100 rows, right? So one thing I haven't mentioned before is that Postgres has a concept of statistics target. And statistics target determines, like, it's a value between, I think, 10 and 10,000, and it determines two different things. First, it determines the size of the sample we use to build the statistics. So if you, by default, it's 100, and if you multiply that by 300, you get the number of rows that will be sampled from the table. So this statistics is built on 30,000 different rows. And the other use for the statistics target is it determines the size of the statistic that is built. So default value is 100, so these statistics have 100 items at most. I will show you why that matters in a minute. So if you want like more accurate statistics, you need to increase this, and you will get larger statistics computed from larger samples, right? So if I now use the two examples from before, so you can see that this doesn't really improve very much, right? It's like still around 10,000, and it's actually 0. The other query here is this one, and that's still roughly the same, right? So what is the problem here? The problem here is that we have the most common value list, but it only represents a tiny part of the data, right? And we still use the old estimate for the rest of the data. So what I can do default statistics target. I will say 10,000, right? I mean, like, that's slightly crazy because it will need like 3 million rows from the table. In this case, it means like the whole table will be sampled and approximated. And it will also create statistic, the most common value list with up to 10,000 rows. So it will be more expensive to do the query planning, right? But the idea is that you can do this on per statistic basis. So you can increase that for single statistic. And then the idea is that the additional query planning is more than outweighed by the reduced execution time, right? So if you increase this the detail in a way that improves the query duration from 1 hour to 1 second, it's probably worth it to spend like 10 milliseconds for query planning, right? So if I do explain analyze, it will take longer. I do have a development build which has like asserts and whatever. So it will take a while. And if I do that again, you can see that suddenly the execution is the estimate is much closer. And if I do the other, it should be also much closer, right? And if I do, I think it's like this, right? So you can see it's almost perfectly exact, right? Because that's one of the larger regions. And yeah, and if I do, of course, drop statistics. Oh, okay, right. Right, so what I have done here, I have changed the condition, the state name to Kiev. So there actually is like, there are matching data. And suddenly it's like 11,000 and 11,000. So it's like perfectly accurate. Obviously, this is like very lucky because the table was sampled as a whole. You will not see that in large data sets, right? But the idea is that in this case, like most of the data fits into the most common value list, right? If I look at the statistic again, sorry, you can see that suddenly instead of 100 rows, 100 groups are represented in this statistic. It's like, well, almost 600, right? So now it represents like much larger part of the data. I could actually show you how much data it represents, because what we have here is a frequency of the data. So I could do this, right? And it represents like 100% of the data. If I do reset the default statistics target, right, this, I will revert it back to 100, right? Right, so I've set it back to 100. If I do analyze zip codes, and if I do the query again, it's like only 34% of the data. So that's the reason why it didn't actually immediately fix the estimations. I need to have like large part of the data in the most common value list. Right. So those are most common value lists. Those are the examples I have done here. So this one is fixed. The other one is also fixed, right? And that was all about the most common value lists. And I will talk about a summary and maybe what's in the future, right? So most common value lists are already in Postgres 12. We have a patch with a different type of histogram, with different type of statistic, which is a histogram. Essentially, replacing the single dimension histogram with multi-dimensional histograms. I'm not sure it will get into Postgres 13. Maybe it will. It's more a question of like how useful that actually is for queries in practice. What I think is much more likely to be in Postgres 13 is like things like statistics on expressions, which we don't really have a good way to do at this point. The only hackish approach, a hackish way to do that in Postgres is to create an expression index. That gives you statistics on expressions, but other than that, we don't have the functionality yet. We also would like to improve estimates of joins, right? So all the statistics that I have shown you so far are for scan nodes, right? So what is the fraction of a table matching a condition? Or how many groups are in the table? But it doesn't tell us, like, if you join two different tables, what's the probability that rows from the two tables match? We don't have a good way to do that. And we don't have a good idea how to actually sample the tables because we can't just do that, independently. There's like a relationship between the tables, like foreign keys or something. That's really difficult. So if you have an idea how to do this, or if you would like to maybe, if you are, say a student of engineering or something, this might be a very interesting topic for like a research. I do have some ideas, but I'm not going to promise anything at this point. We have the only thing that we have for that is the syntax, right? So we have designed the command in a way that allows this. We know we want that, but we don't have the code for that. And that's all from me here. If you have any questions, I'm available now or later. Although I heard there will be beer, so I'm not sure. You can try. You can try. Yeah. Anyway, these are my email, Twitter, whatever. So if you want, maybe you can ask me later in the future, right? Right. So, well, that's all from me.
Thank you, guys.
Any question?
Doing select, explain, or when inserting data, and when it is updated automatically.
Okay, so the question is, can we create the statistics automatically? We don't have the capability at this point. It's something I would very much like to do. We have some experimental extensions that kind of will give us the data, right? Because what we need is information like these combinations of conditions are frequently misestimated. And then we can pick and say, create the statistics, and hopefully that will improve the queries. The first step is actually collecting the data. And we don't have anything like that in Postgres. There is, I think, an extension from Dalibo, which is called pgQualStats, which does something like that. I hope to use something like that and actually do, well, not create it automatically, because there is always the problem that you may actually break other queries, or you may, the analyze may get slightly more expensive because you suddenly need to sample or build additional statistics. So I don't think we want to do that fully automatically, but we might actually provide feedback to the users and say, well, these conditions actually maybe you want to create the statistics, like a paperclip, or say like, it seems you need a statistic. So that's something I'd like to see in Postgres. If there is anyone willing to work on that, I think that might be actually a fairly isolated part of the code. So it's maybe like a good for people who want to start contributing to Postgres, right? Because it's like very isolated. It doesn't immediately touch critical code. It could be done from an extension, for example. So I'm happy to help people with development like that.
What about update?
Sorry?
What about update and maintain? How is updating?
So it's up. You mean the statistics?
I mean this new statistics. Is it updated when you just run analyze?
Yes. It's part of analyze. It's part of auto vacuum. So just like regular statistics, it's going to be updated automatically, right?
One more question here.
Yes.
Yeah, what's the cost
So it's definitely not free, but I don't think I haven't seen. So there are two parts, right? One is like building the statistics during analyze, and you have seen that actually it can take quite a bit of time, right? I think there's like room for improvement, but it's not like a huge issue because it usually happens in the background in the auto vacuum something. The other question is like, how does it affect queries? I don't think you will notice that because we only use the statistic when you have conditions matching the statistic, right? So we quickly eliminate statistics that we can't actually use. I don't think that's going to be an issue. Obviously, if you have a database which doesn't need the statistics, which will not get like significant improvement from that, you will not create the statistics. And if you need the statistics, it's usually the case that the query is running for 1 hour instead of 1 second. In that case, like adding a little bit of like 1 millisecond of extra time for the planning, it's probably a good investment. I don't think it's going to be an issue, right? For OLTP workloads, you probably don't need the statistics at all because you usually work with small amounts of data anyway, so the misestimates are not that bad. This is mostly for like analytical databases, and in that case, the query planning may already be quite expensive, and this additional overhead is like negligible because once you start joining like 10 tables, just searching for the query for the join order is going to be fairly expensive. So I don't think this is going to be noticeable.
One more question here, Thomas. It's actually a two-part question. First, how to choose? Any recommendation on choosing the default statistics or setting statistics for a table? And the second one is any real-world scenarios, more real-world scenarios where this thing can benefit?
So first question, how to pick the right statistics? Well, I think it's very similar to how you should approach indexing, right? I mean, should I create a new index or not? Well, you should have a feeling like which columns are dependent, but then you should also look at slow queries and see, well, why is the query slow? Like, is it misestimated or not? If it's not misestimated, then you shouldn't create statistics. If it's misestimated, is it actually causing issues or not? I don't have a very good idea how to. That's one of the reasons why I don't want to create fully automatic statistics creation, because it really depends of not just the single query, but it depends on the workload as a whole. And maybe you want maybe fast analyze is more useful for you than a query which instead of 10 seconds run 1 second, right? I don't have a good answer to that. And a practical use case, or, well, I think if you are struggling with slow queries that are caused by misestimations, which is pretty common, especially as we are working with larger and larger data sets, which are denormalized in some sense or contain, redundancy naturally. That's why I started working on that. I mean, like, it's not that I just thought that we should implement statistics. It's actually based on real world issues, right? So we had a number of customers who were having issues with the aggregation running out of memory because they had like skewed or strange data sets where the cardinality estimation was giving them the wrong answers. So they needed actually this, because either they had to decrease the work mem to force the database to use a group aggregation, and then a lot of stuff was slow, or they needed to somehow improve the estimates, right? And so I think it's actually very practical. And it's not like Postgres is the only database collecting statistics like this. I know that, for example, Oracle also has ability also to collect something like this, but people often don't know about it.
Okay, we will have time, sorry, during this break and after
Okay.
party. And,